As, as Tudor just said, I'm going to be talking about building software at scale at Thought Machine. So I'm going to be talking through some of the issues that we've had and how we overcame them, and some of the open source tooling that we've built around that. So as I said, I'm Peter. I'm the CIO of Thought Machine. So Thought Machine is creating Vault, which is a next generation core banking system. So that's the system of record for financial transactions and user accounts in a bank. So it's a very critical part of what banks do, and has traditionally been the domain of mainframes and COBOL and all sorts of horrible things like that. So we're trying to bring them into the 21st century and provide them with modern technology. So what do I do at the company? So my team looks after infrastructure, so production infrastructure, so things like Postgres and Kafka and Istio that sit underneath Vault, things like releases and testing, and CI and build tooling. And this talk is going to focus around the last one of those, and as I said, some of the open source work that we've done to support this. So what does it mean for us to build software? So we have about 200 engineers at Thought Machine now. So they're actively coding. They're building Vault as a microservice architecture. So they're actively coding on over 250 services. And we develop all of this in one Git repo, a monorepo. This is approximately 3.1 million lines of code now. So there's about 112,000 commits in it. That gives you a little bit of a sense of the scale of what we're dealing with. And that leads to about 150 merge pull requests every day. So every one of those pull requests is tested exhaustively pre-merge and then auto-deployed to our development environments as fast as possible. So once upon a time, we had a single build that did all of that. But at the scale we're at now, that just doesn't work. The one single build became a huge drain on our development and took way too long to get it through. So it could literally got to the point of taking hours to get people's code into production. And that's not how we want to work. We want to be faster than that. So we have a bit of a flow about how code gets built at Thought Machine. So our developers work away, they send a pull request. That pull request, we automatically run tests against it and verify that it's good. And it goes out for code review. So all of our code is reviewed by other engineers before it's submitted. So code reviews, as you all probably know, is a super important tool to both ensure the quality of code for people to make good suggestions about how to improve it, but also to spread the knowledge about how it works to other people in the company. Then after the code has been reviewed and merged, it's then automatically built and deployed to our development environments. Now, that sounds kind of simple, right? So what's hard about that? So we've got two parts of this that are done very automatically. So the running the tests, and the question there is which of the tests should we run? We've got lots of them, as I'll come back to in a bit. And then the building and deployment. So, how do we do that efficiently? Do we need to build everything, or do we just build some parts of it? So the efficiency here is pretty key. So on a small repo, just running all of the tests is a pretty decent strategy, right? But in the repository I described before in our code at Thought Machine, we've got around 100,000 test cases. So running all of those end to ends can literally take hours, right? This is running the kind of the whole gamut of tests, from very small, fast unit tests to bigger and heavier integration tests that can take quite some time. So what we want to do is identify and run just the relevant set of tests to the change that has been made. And similarly, we'd ideally not want to build everything after when we come to deploy it. So we want to be able to reuse work that we've done before. These kinds of issues are the domain of the build system to solve. So that's really the system that should be able to answer these questions and do these things efficiently. So the build system that we use is called Please. So this is an in-house system that we've created. It's designed to prioritize correctness and speed, and it works across all of our languages. So that's Go, Python, JavaScript, and Java, and TypeScript as well. The front-end guys have been doing a lot of migration to that. So it provides a single consistent interface across all of these languages. So you can write please build or please test at your command line, and you don't have to know or care whether you're running a Go test or a Python test or whatever. We came up with the idea of Please in the pub one evening. So obviously that's a traditional site of British innovation. And, you know, we asked ourselves all the traditional questions like how hard can it be and that kind of thing. This ended up being a big success for us. It's introduced the company to Go, which is now our biggest programming language, and also became our biggest open source project. So obviously the performance of something like this is super important. So there's this classic argument that, you know, programmers, what do? You're sitting there coding away and then you have to wait for something to build. That's downtime. You're waiting for your code to compile. And, you know, people wander off. They probably don't literally have sword fights on chairs, but they might. But, you know, you go away and check your email or something, you get distracted and you come back. And when you come back, your flow is a little bit broken. So the faster you can do this thing, the faster you can turn it around, the more productive our engineers are, and the happier they are. So this is a really high priority thing for Please. So a little bit about how Please works as a system. So it stores its metadata in build files. So these are kind of analogous to make files, or if you've used something like Gradle, this is build.gradle or pom.xmls for Maven or whatever, right? There's lots of build systems out there that typically have metadata in these files to describe relationships between the different things that can be built and instructions about how we build it. In Please's case, these build files normally take the form of declarative build instructions. I'll show you an example of one in a moment. But it's actually a real programming language, and it's a custom in-house programming language that's implemented specifically for it. It's a syntactic subset of Python with some sort of slightly different semantics and designed to be more deterministic and do a minimal set of things that we need. And having these files and the consistency of them is key to being able to work consistently across all the different languages that I described before. So here's an example of a build file. This shows just a small snippet of a couple of Python files. So you have a Python library, so that's a logical unit of Python code, and a test on it, which is described as a Python test. And in each case, we define the sources that these things are going to operate on and dependencies between them. We have this kind of distinctive syntax, this double slash and so forth. And that's a way of referring to these different targets either within this build file or in another part of the repository. And so all of this can be parsed by the system very efficiently, and it can understand the relationships between these different things. And that becomes a key building block to all of the work that we're able to do with the system. So this gives you a little bit of a flavor of what it's like to run. So this is a little animation showing what Please does when you run it. This is me running it on my dev workstation yesterday, I think, where you can see it's going away, building a whole lot of different things, orchestrating a lot of different build targets across a subsection of our repo. All of these things are being built in parallel, and it's basically scheduling all of this work and ensuring that things are being built as fast and as efficiently as possible. So a critical property is this concept of dependencies that I mentioned before. So we're very explicit about what we mark in these build files, and that means that whenever someone changes something, we can always know exactly what will be affected by that change. So that lets us answer the first question that I raised before. You know, how do we know what set of tests to run? Well, it turns out that when you've got a principled system like this, it's actually quite easy to answer that question. In Please, you can literally run Please query changes, and it will tell you all of the things that have changed. And it will give you then the list of everything that we need to run to be confident that our pull request hasn't broken any tests and that everything's going to work. And again, this is in a lot of kind of older, more traditional systems. If you're using Make or something, it's not really able to answer these questions in the same way. So this is a really, really powerful thing and a fundamental building block to a lot of what we do with it. Then the other question I raised before was, you know, do we need to build everything? So clearly the answer is no. We might have built some things before, and the knowledge of this and how to do it is built into Please. So it has powerful and very critically correct incrementality. So it only needs to rebuild the minimal set of things that have changed each time versus what it's done before. correctness is a really important concept for this kind of thing. So our developers have to trust that it will do the right thing. And if you've ever worked on a system like this with a build system that isn't correct and sometimes does the wrong things, you're always second guessing it. Something goes wrong and you think maybe I need to do a clean build to get the right answer. And our goal that we're pretty sure we've achieved internally is that our developers never need to question this. They're confident that Please will always give them what it should. And it accomplishes this by using hashes of the file contents to identify changes of everything. So again, like older systems might have used timestamps or something like that. There's a lot of ways that can go wrong. And we instead do it by tracking everything by hashes, which means that we can be totally confident that we know exactly what's going in and when something changes. So going back to the flow we had before about how code gets built, we've figured out how to do these tests quickly, and we figured out how to do the builds and deploys quickly. So as I said before, when we had a single monolithic build, this was about sort of up to maybe a couple of hours or something like that, and by applying things like this and sharding up parts of our build, we got it down to about sort of 5 to 10 minutes, something like that, for people to submit their code and get it into production, which is obviously a huge improvement and a big quality of life improvement for our developers. And that covers most of what Thought Machine was doing up until maybe about a year ago or something like that. So at that point, the company started getting even a bit bigger again. We were pretty efficient about this stuff, but we were now starting to bang into the limits of what we could actually do on a single CI machine. So we provision all of this in the cloud, on Google Cloud, and our CI machines are about 16 CPUs. We've got about 20 to 40 of them, something like that. So we can parallelize by increasing those, but it's really not practical and not efficient to increase the size of the individual ones. We obviously start paying quite a lot of money for it, and we're not making good use of it. A principal solution to this is to spread this build across multiple machines. So within each of them, we can submit individual build actions out to different servers that are then able to execute them and send the results back. So there's an open API for this, and there's a link there in the talk on GitHub, of which there's a community of us, a small set of build systems that are making use of this to be able to talk to a set of common servers that can provide this execution for them. This is all based on gRPC, which is a pretty neat bit of tech that came out of Google for doing fast, efficient communication between services. So the way that this works is basically, for a developer, they're sitting there coding away on their machine, and when they run Please Build, it now transparently sends the request up to a set of servers, uploads whatever files it has to. Those servers distribute the work out to any of the other dev machines in the office. So each of them might get, say, like one action out of the hundreds that need to be performed. They execute it and send it back. So now at this point, we're not limited by the size of any one machine. This is more limited by the total size of the fleet, which, for us is pretty big, so we've got quite a lot of developers. So this obviously has a really nice property of scaling with the size of the company. As we grow, the amount of compute here goes up. We also have what we call a hi-fi deployment, so a high fidelity deployment on Google Cloud that we use for building release artifacts and so forth. So that's about something like 400 to 600 CPUs worth, so there's quite a bit of power there. The lower fidelity one that we use for local development around the actual developers' machines is actually a little bit bigger. It's about 1,000 CPUs now or something like that. But obviously we try to limit how much we do with them, so the developers are doing other things with their machines as well. There's a lot of advantages here besides parallelism as well. So this leans very heavily on distributed caching, which means that everything only needs to be built once. Right? If I need to build something, lots of things have already been compiled by someone else somewhere in the company, and my machine is actually pulling down results that have already been calculated. It means our developers don't get big CPU spikes, slowing down their dev machines. So, needing to compile a lot of things and suddenly needing a lot of CPU can obviously slow down the interactivity of the machine. And it also means the builds become very highly deterministic. So if different machines are producing slightly different actions because they're embedding like timestamps or local paths or something, these typically in this remote execution scheme, you tend to agree on it a lot more because you're not rebuilding things on every single different machine. So again, this all plays into making all of this efficient and making it as fast as possible for our developers. So again, going back to this little animation I showed you before, this is Please running in remote mode, where you can see it. You can see part of at the top kind of moving up and down, where it's actually executing some things on my machine. So for various reasons, some actions can request to run locally on a machine, and it's actually seamlessly stitching this work back and forth between some local work and a much bigger fleet or a much bigger set of remote pieces of work that are being submitted off to other machines, where there's about 100 of them. So there's actually more than I actually have room to show in the terminal window where I was reporting this. But obviously that makes a huge difference to the speed at which it can get through this stuff. So quickly about the Please project. So Please is all open source. If you want to know more about it, you can find out more on the website please.build. Which you can see there in the slides, or you can check out the code on GitHub. So that's github.com/thoughtmachine/please. If you're interested in the company in general, then you can find out more about us at thoughtmachine.net, or we are Thought Machine on Instagram, which shows slightly more of the sort of fun side and some of the things we get up to when we're not actually developing so much. So I hope that gives a little bit of a flavor of some of the problems we've seen here and some of the ways we worked around them. If you're interested in that, please do get in touch. But for now, I guess for anyone that's following along, do we have any questions?
Hello again. I'm going to be taking the questions from the people. We do have a couple of questions. The first one was asked a bit earlier, and it was, is Please open source, which I think you answered at the end of the presentation, so there's no point in answering it now. Then we had another question.
Sure.
Does parallelizing not increase the errors as each machine can fail individually?
So it doesn't increase the errors in terms of we're very careful that when it fails, the worst thing that can happen is it can fail to build a thing. So it never fails by building something wrong, which would be quite catastrophic. In general, though, no, there's a little more complexity in managing like a distributed fleet of machines versus just running something on one machine. But it actually tends to increase the reliability because we were seeing a lot of issues around tests. Like if we let's say we're running 10 tests at once on a local machine, sometimes we'd see issues with tests failing due to like resource starvation, like the running out of CPU or thrashing the disk too heavily or something like that. In general, it tends to make it more reliable because rather than centralizing it on one machine, we're spreading it out across lots of them, so you don't see so much contention around that.
Okay, I think that answers it. The next question is, do you have any statistics about the efficiency of Please?
That's an interesting question. In general, I guess it's a little bit hard to do like a proper A/B test because obviously at this point we're way past being able to kind of swap our systems to some other kind of build system. In general, I think we're seeing it's well over 90% reuse of build actions. So when our developers are sending pull requests and so forth, like literally 90% of the things that it would do have already been done by another machine and are getting reused by that thing. So this is obviously a pretty huge thing, right? We're well past the point of being able to keep up with our developer demand without some of those efficiencies in place, or at least without us paying a whole lot more money to Google Cloud to provision a lot more machines for it.
Yeah. Next question. Why did you make the decision to migrate from JavaScript to TypeScript?
And I'm probably not quite the best person to ask about this. So our front-end team they've got a little bit of a mix of both. So they've still got some JavaScript around, and they've got a lot more TypeScript. I think they like the type safety. They like the community around it, so I think TypeScript's been kind of quite widely embraced by a lot of parts of the community. But in general, I think we see a lot of trend to this, particularly in bigger projects. As I mentioned before, like we have quite a bit of Python, but now we have more Go. Even on the Python side, we're starting to introduce type annotations and that type of thing. When you get to a certain scale, it does become easier to work with these things when you've got a bit more of that information, which is an interesting thing. And I really enjoy dynamic languages like that, where it's very easy to get started, very easy to script something out. But your considerations when you're working on a team of 5 or 10 developers who aren't so familiar with the code are a little different. And so I think the advantages of TypeScript being more explicit about that stuff were probably really, really good for the front end guys. I mean, they've definitely found it a big win.
Yeah. Next is, does the overhead for so many parallel machines not become inefficient at some point?
So there is inefficiency. There's more latency doing it this way. Running an individual build action takes longer because you have to move files around over the network. We've spent quite a bit of time optimizing this, so we have to be quite careful about like where things are placed on the network, and be careful not to send too much stuff like in and out of the office, for example. There isn't a lot of inefficiency due to having too many machines. So the more you've got on the fleet, basically, the better the scheme gets. But it wouldn't work very well if you had only 10 of them, for example, right? At that point, you'd be better off doing everything on your local machine and not paying the network overhead. So the parallelization actually gets better the more of them that there are.
Yeah. We've actually got a couple more questions. First, when tests are they run locally or across all the machines?
So tests are distributed across all the machines as well. So we treat running a test as very similar to running any other build action, right? The test executes, it runs, it produces some results files, and then we bring those back and interpret them. So they're distributed across this fleet as well. And that's pretty important. In general, tests tend to take longer to run than a lot of the sort of individual compilation steps would. So distributing them is at least as big a win as distributing the rest of it.
Yeah. And one last question. How does Please handle building artifacts from different languages?
So Please we designed it deliberately to be very generic. So the core of it doesn't have a lot of knowledge of the specific languages and how to build them. That's all handled in the actual build language itself that I described before. So you can very easily program it to accept different languages, and it treats everything as very, very generically. So the build action for let's say Python might be running and doing a little bit of type annotation, and we produce a little zip file from it at the end. Similarly for Java, we produce a Jar file. For Go, we're compiling like binary artifacts or something. But Please doesn't really care about that. You just tell it like this thing is going to run and it's going to produce these outputs. And at the end of it, it gets those back, and it can run all of those very easily. Obviously, you're still limited by how much each language can fundamentally interact with one another. So if you're programming in, say, Java and Kotlin, you may be able to very easily take those two and put them together and integrate them. Obviously, you're going to have to do a little bit more work if it's, say, Java and Python. Please doesn't, unfortunately, magically solve that problem for you.
Yeah, okay, looks like that's it in terms of questions. So,
okay.
Yeah, since we're not getting any more now, then thank you very much, Peter, for coming to our event. We hope you enjoyed it. We definitely enjoyed having you. And yeah, well, thank you very much for
thanks very much.
hosting such a great talk. And now that this is done, it is, I think, time to move to the next section of our event, which is the one regarding constitutional changes.